So this is the flipped content to do with electron transfer reactions. I'm going to kind of start with just regular electron transfer reactions, but I'm actually specifically going to talk about electron transfer reactions which are enhanced by absorption of light. So this is a really important area. Chemistry is electron transfer reactions. Everything we do in chemistry is to do with moving electrons around, forming and breaking bonds. But we have a lot of modern uses of not just the formation and the breaking of bonds or moving electrons around, however we wanted to call it, but by doing that by absorption of a photon. So things like photovoltaics, like light harvesting for solar energy, really, really important. Looking at how plants manage to collect the sun's energy in photosystems 1 and 2. My personal background is looking at DNA damage, looking at how DNA is damaged by absorption of light from the sun. And Frank is going to talk about energy capture and things like CO2 reduction in his lectures. And so this is kind of a bridge between what I teach and what he teaches. So in general, what is an electron transfer reaction? Well, normally we would talk about an oxidizing agent and a reducing agent, but I'm going to change my terminology slightly to match the terminology we've used in our photochemical studies. So instead of an oxidizing agent and a reducing agent, I'm going to have a donor and an acceptor. So my donor is going to donate electrons, and my acceptor is going to accept electrons. And so in this case, I have a donor and an acceptor, and I move my electron between the two of them, resulting in a formation of a cation and anion. Now this happens because of the relative alignment of the energy levels on my donor and my acceptor. So I have my donor, and what happens is the HOMO, the highest occupied molecular orbital on the donor, is higher in energy than the lowest unoccupied molecular orbital on the acceptor. Therefore, there's a net kind of gain in energy, or kind of lowering of the overall energy of the system, if I transfer an electron between the donor and the acceptor. This means that I can do work in my system. If I start to look about what happens when those orbitals aren't quite so well aligned, in this case I have a donor and an acceptor, but it's not going to be so easy for me to form the cation and the anion because my energy levels don't align such that the HOMO on the donor is higher in energy than the LUMO on the acceptor. But I will notice that the LUMO on the acceptor is lower in energy than the LUMO on the donor. Now in this case, if I excite my donor, I can then transfer my electron into that lower energy level of the acceptor, and I will see that same net electron transfer process occurring. There's another way I can do the same thing, and that is by exciting an electron on my acceptor. And you will see that in this case, the HOMO of my donor is higher in energy than the now half-filled HOMO on my acceptor. And so I can move an electron in that way as well. Both of these mechanisms are just called photo-induced electron transfer. I can also have a final system where one of my pair has a lone electron. So in this case, my donor has a lone electron sitting in its LUMO, what would be its LUMO orbital, and that electron can move to the LUMO orbital of my acceptor, and this is just called electron exchange. So I have various different electron transfer processes by name. Intramolecular electron transfer is where we have my donor and acceptor as basically different parts of the same molecule. Now this is very common because if I have them as different parts of the same molecule, what I can do is I can facilitate that electron transfer, but it's what I do with it afterwards that becomes the important part. Or I could have intermolecular electron transfer, where I need to have two species involved. Now, increasingly we want these to be solid state reactions, and so the following definitions, inner and outer sphere, don't matter so much. But if I have solution phase things, I start to have diffusion effects that that can really kind of curtail the rate of reaction. If I have solid state things, that's not so important because it's not based on collisional theory. And so I have basically the difference between inner and outer sphere, where inner sphere reactions are essentially reactions that take place when I've got a strong covalent bond between the molecule, or a strong, perhaps ionic interaction between my molecules taking place. Whereas outer sphere is a much weaker, just a kind of a dipole interaction, or just, you know, a London kind of dispersion force interaction between my molecules. So some thermodynamics of what's going on. Now this equation that I'm showing you at the bottom is called the Rehm-Weller equation, and that's linking the redox potentials of my donor and my acceptor to some properties of the molecules. So I have the difference in redox potentials of my donor and acceptor. I have this kind of WR term at the end, or omega R term at the end, which is basically a work function. And I have this E00. Now E00 is basically the energy I get when I excite an electron into the LUMO orbital. So how much energy do I need to take? And my Gibbs driving force is given to me as a property of all of these. This means that if I can get energy in the form of light, I'm not having to provide it as chemical energy, and therefore I can make electron transfer reactions happen that wouldn't unless I had absorbed a photon. So in this case, I promote a donor by absorption of a photon of light into the LUMO, and it's basically the energy difference between the HOMO and removing the electron to an infinite distance in a vacuum, or what I would call my reduction potential. Now this E00 term is this energy difference between my HOMO and LUMO, or how much energy I've been able to put into the system to help it on its way, so that I don't need to overcome that in other methods. This Rehm-Weller equation is really important. It tells me how much energy I can get out of my system, how much energy I can store as well. And now I'm not just talking about general terms about this wave function and that wave function. I can actually link it to a thermodynamic property, the driving force delta G, for my reaction. And delta G tells me the maximum possible work I can get out of my system. Solvation becomes really important to consider when I have movement of electrons. The reason being is that if I go from a non-charged to a charged species, there are going to be great differences in how that will behave in polar and non-polar solvents. So if we think about this in terms of the Franck-Condon principle, here I have a electron exchange kind of reaction. I'm already carrying a charge on something. And if we just use the basic principles given to us by the Franck-Condon, which is essentially electron transitions occur very rapidly, considerably more rapidly than molecular vibrations, or they can be shown as vertical on energy level diagrams. This means that my solvent around my molecule and my molecule itself does not have a chance to change or rearrange in the course of the electron transfer reaction. So as I move the electron, I am effectively kind of capturing my excited state in its non-idealized, non-optimized form. I then have to let that same Franck-Condon principle take effect. Now I'm in the excited state, things will change and relax. And that means that I am able to kind of give things time to restructure, or I can end up lowering the energy of my system again. It's exactly the same as the Franck-Condon principle we learnt for a Stokes shift, but now I'm actually talking about it in terms of movement of an electron between a donor and an acceptor. If I think about all molecules existing and being able to be modelled as a potential well, just as we've done in are studies with things like harmonic oscillators and vibrations within molecules. Then I can model my donor and my acceptor as two potential wells. And depending upon the redox potentials, these potential wells are going to align with each other in different manners. In this case, I have an isoenergetic reaction. In other words, delta G is 0, or the potential wells line up at the bottom. And I'm going to have an activation barrier for this. I can't get from the bottom of the pink well to the bottom of the green well without going over a barrier where the two lines cross. This parabola, if I go from the bottom of one potential well vertically upwards, I get this this parameter lambda given to me by the properties of the parabola. This parameter lambda becomes an important process in what we're going to study, and it's called the reorganization energy. The activation barrier is just 1/4 of this reorganization energy within my molecule. For this case where I have an isoenergetic barrier. So this is now my same figure as I've just seen, my isoenergetic electron transfer reaction. If I instead move to a system where my acceptor is lower in energy than my donor, I can start to see that my driving force for my reaction is going to change, as is my activation barrier. And if I continue with this same scenario, I can reach this point where this reorganization energy, lambda, is the same magnitude as delta G, or minus delta G is equal to lambda. This is a really interesting point, because if you think about this being the point where the two lines cross is the activation barrier, then I can see in this reaction there is no activation barrier, or all of my electrons will spontaneously move across with no barrier to their doing so. If I also think about the consequence of making my acceptor even more good at accepting this electron, more negative of potential, then I can start to see that I actually reintroduce an activation barrier. Now I have a difference between the bottom of one potential well and where the energy crosses, where the two parabola crosses, or where my activation barrier is. This is a really important consequence. Not only am I linking my driving force for my reaction with my kinetic parameters, something which I haven't done before, but I'm now also able to reach this point where the driving force of the reaction is limiting how fast a reaction can go, or more precisely, how the reorganization energy in a system limits how fast a reaction can go. This is a really interesting concept. It means that the more spontaneous I make a reaction, the further down I can slow it down, which is perhaps counterintuitive, but won Rudolf Marcus the Nobel Prize in the 1970s. So fundamental was this observation from Marcus that it is now a very interesting part of chemistry. The fact that if I increase the driving force of a reaction, I can slow down a chemical reaction is so counterintuitive, it took years for people to actually prove it experimentally. But now we're understanding systems like photosystems 1 and 2, or DNA damage and electron transfer along DNA. It's becoming a really interesting area. The Marcus equation is one of those other equations that, whilst I'm showing it you here for interest, I will not expect you to know and learn. However, it's interesting to note some of the factors which will affect the rate of a reaction. I can see that the rate of a reaction is dependent upon temperature. In a quite a complicated manner, in fact, it's 1 over the square root of temperature, and then and then an exponential raised to minus 1 over the temperature. It's also related to this lambda, this reorganization energy, or the difference in structure between my reactant and product state. I also have this term in here, which is called V. V is my electronic coupling element, and I can think about this as the overlap integral between the two states in my system, where VR naught is equal to the kind of the minimum system where there is a complete overlap between the donor and the acceptor. when they're as close as possible that they can be. This rate of electron transfer also depends upon the separation of the donor and the acceptor. This is again common sense. As I increase the separation, I would not expect the rate of electron transfer to increase. Such a fundamental equation and dependent on so few variables is actually really interesting that we don't teach you it until a third year course. If I'm just take the Marcus equation, and I've simplified it down here to just look at different values of this parameter beta. So we can see this term beta appears in this equation here with v, the overlap integral, and it's got this separation term in it. B is basically a measure of how quickly the electron transfer drops off with distance. And so we can see that as we have different values in B, I see very different effects on the rate constant for my electron transfer reaction. This rate constant of electron transfer here can be substituted into my quantum yield equation to give me another pathway of how energy is lost within my system, or another pathway for how photons are decayed from an excited state. Now, I've already kind of alluded to the fact that we get this interesting region with Marcus, where if I increase my driving potential a long way, I no longer see a rise in the kinetic rate, I see a maximum. Now, being able to measure this is very, very difficult. Getting the experiments to do it properly is very, very difficult. Ultimately, I can't do this if I need reactions to diffuse together. I just can't reach the Marcus inverted region, as we call it, or this region where the kinetic rate slows down. So you have to do it by using fixed systems. So a donor and an acceptor which is held somehow rigidly. What I tend to see is this observed kinetic rate, where my Marcus region just levels off. This is an effect of the reorganization energy and an effect of diffusion for when that is the case. If I want to reach the Marcus inverted region, I need a very large driving force in the region of 250 kilojoules per mole. It's therefore very difficult to reach by most methods. However, for photochemical reactions, or reactions where I've induced chemistry to happen by absorption of a photon, it's much easier to reach. It's also considerably easier to reach if I work in rigid or viscous media. If I think about some of the things I've already been talking about, such as solar cells, or photosystem 1 and 2, or DNA damage, these are all rigid media, which is why Marcus electron transfer becomes increasingly important for all of them. The following is a rather nice experiment where they looked at the difference between a donor and an acceptor, and they would separate the donor and acceptor by a rigid kind of structured backbone. What they would do is they would change the length of this backbone, and they would be able to study the kinetic rate for this electron transfer reaction. In this case, everything was excited using absorption of a photon before they could measure the kinetic decay. The data presented here, although it doesn't perfectly mix with the line, is almost certainly not a straight line, and actually shows this decay in the rate constant for electron transfer as I decrease the size of this spacer. It's a really, really interesting and important piece of work, and is massively important when we start to consider chemical reactions, because ultimately we don't want to make them too good. We want to optimize them so that I can get the fastest possible reaction and the best separation of donor and acceptor electrons. So I'm going to finish this kind of flipped lecture just with an example of some of the work that I did. So you know I have an interest in DNA. I don't expect you to know a huge amount about DNA other than the fact that it is a rigid biological molecule. The backbone of DNA is negatively charged. It has a groove. All very interesting. What I'm going to do in this case is I'm going to take just a small piece of DNA, 15 base pairs long, and I modify one of the bases. So I'm modifying the base using the common oxidative damage legion of 8-oxoguanine. Now, interestingly, 8-oxoguanine is in all of our bodies. If you're a smoker, the chances of you having it are greatly increased. So for most people, it's about 4 in a million, I think. 4 in 1,000 guanine bases appear as 8-oxoguanine. If you're a smoker, this more than doubles. Now we can see, if I start to do this, if I then instead put an acceptor molecule in, so what's going to happen is the damaged base, this 8-oxoguanine, is going to be my donor, and I put an acceptor molecule in, I can start to see quenching of the fluorescence of the acceptor molecule, and I can then look at how well DNA can conduct electrons along its structure, or more precisely, how far DNA damage can migrate along a piece of DNA. So I did this first off with including one piece of damage, and then I increased it to having 4 of these modified guanine bases, and I also had a kind of a background where there was no damaged DNA. And I just have my normalized fluorescence. That just means I'm comparing one to the other. When I had no damage, I can see that the lifetime of my DNA is the lifetime of my fluorescent molecule is 2.8 nanoseconds. When I put in a single piece of oxidative damage, or this 8-oxo-G molecule, then I can see that my lifetime decreases. My lifetime decreases because I have put in another pathway into that quantum yield calculation. In this case, I can see that my normalized fluorescence drops to 0.558, and my comparison of my lifetimes has dropped to 0.85. If I instead include 4 of these back damaged bases, I can see that my normalized fluorescence has dropped and my lifetime has dropped, but they're at different rates. This is really interesting in a couple of aspects. One, I'm definitely seeing damage caused to my DNA. Secondly, that damage can't travel far. This is only a piece of DNA, 15 bases long, and effectively, if I put in one of my dye molecules into this, not everything starts to be damaged. I don't see electron transfer for every reaction. I don't even see electron transfer for every reaction when I have 4 of my guanine bases. So ultimately, our DNA is quite good at protecting itself from oxidative damage, particularly when it's photoinduced. So I'm going to finish this with just one of my my kind of concept questions. So electron transfer reactions don't normally slow down with increasing driving force because thermodynamics and kinetics are completely unrelated. B, the Marcus inverted region only occurs at high values of lambda. C, reactions from excited states only depend upon the excited state lifetime. D, there needs to be an excited state on both the donor and acceptor, which is uncommon. E, vibrations within molecules occur much faster than electron transfer reactions. Or F, the Marcus inverted region only occurs at very high values of delta G naught. I'll leave you for a few seconds to think about this, but I encourage you to press pause to think over this question. Whilst almost all of these statements are indeed true, the answer is actually F. The Marcus inverted region is only at very, very large driving forces, or when I've managed to kind of reach that point where there is no activation barrier and I move beyond it. Thermodynamics and kinetics are considered unrelated at lower levels, but there's actually a fundamental link between them. And it's really important at this level to understand how strong that link is. I hope you found this interesting. If you've got any questions, please ask me.